Hello, everyone. I'm Catherine McGeoch. I'm really happy to be here. This is my nth Qubits meeting. I guess I clicked ahead without realizing it. That's all right. I think many people know I'm actually retired from D-Wave. I'm no longer a full-time employee of D-Wave, but I've got the best job in the world as a part-time contractor to D-Wave. I get to pick my projects and write papers and give talks, so it's way, way better than actually working for the man. But for 10 years, I was on the benchmarking team at D-Wave, and it's a group within the company that's pretty much charged with evaluating the performance of whatever they put in front of us, and if it's hardware, seeing how well the technological innovations in the hardware map to actual performance in practice and things like that. And it's a great gig. It's been a lot of fun, and I still get to hang around and talk about it. So, but because of my role at D-Wave, the thing that everybody wants to know is, what about performance? What can you tell me about performance? They stop me on the street. What? How does it perform? And the two main questions are, under what circumstances does an annealing QPU outperform classical heuristics, classical alternatives, and are they going to be able to scale up? And the fact is, for a long time, I was really reluctant to say anything because it's all empirical. We don't have good models for predicting and scaling beyond the data we have. And it's sort of been, well, sometimes it works, sometimes it doesn't, but it's been hard to come up with a more precise explanation or an understanding even of why sometimes we see great performance and sometimes we don't. Until very recently, my colleague Pau Faré at D-Wave and I wrote a paper about, we called it quantum utility before IBM reused the word. More recently, I've been working on a literature review where, really just going back over the past decade and looking at all the different papers about quantum annealing performance. And as it turns out, there are some patterns, and I'm finally in a position, I'm delighted to say, where I can actually, draw some lines. This is going to work, this won't work, and so forth. So I want to talk a little bit about that. And as it turns out, it's kind of surprising, or it was surprising to me, the places where the lines get drawn, and so I'll talk a little bit about that. In order to talk about that, let me just sort of explain two kind of key concepts that are useful to understand. One is the notion of a logical input versus a physical input. The logical input, these QUBOs or the Ising model problems, they're defined on graphs, and the logical input is the original graph. It's got some structure, and it's just a regular old graph. And that graph has to be mapped onto the hardware topology, the actual arrangement of qubits and couplers, and that's a process called minor embedding. And then you get a physical graph. And what happens is, usually or often, when you're starting out with a logical graph, you get some number of nodes, that's your problem size, and mapping it onto the physical graph increases the problem size. You have to map a node from the original graph into what we call a chain of qubits in the physical graph, and there could be more than one qubit per node, and so it makes the problem harder because it's bigger, one presumes, and you get a different. It matters to your understanding of performance which of these kind of graphs that you're looking at. In particular, classical solvers, as a general rule, they can just work on the smaller logical graph, without having to embed it. And so they can maybe get a performance advantage because of the fact that it's a smaller problem. The other important concept is anneal time versus access time. And anneal time is like the pure quantum computation. It's the time you set in terms of the anneal. It can range between, until about a month ago, between 2 microseconds and 2,000 microseconds, so about a millisecond. Nowadays, with fast anneals, you can get that all the way down to 5 nanoseconds, but all of the previous work all of the benchmarking work has been in that higher, not fast anneal regime. And so that's a very short runtime. You would measure that if you're really more interested in the algorithm performance, in the heuristic, the pure computation time, and you're thinking of comparing that to the pure computation time of some classical solvers. And the other thing you could measure is access time, and there's some system-induced overhead to the computation time that has to do with programming the chip. It's about 20 milliseconds. And then reading out each solution takes about 200 microseconds or 0.2 milliseconds. And so I made a diagram here that more or less shows, maybe for a, this is just made up data. I'm just using this for diagram. It's not real. But, at maybe a problem size around 1,000 variables or something, what happens is, I put 2 example classical algorithms. A greedy solver, it just picks a random solution, rolls downhill to the local minimum, pick a random solution, roll downhill to a local minimum, so forth. Those are the green dots there. And you can bang out greedy solutions pretty quickly, and so you get a cloud of points that is pretty much the sample of the distribution of solutions that are in local minima that can be reached by random starts, okay? So you see this cloud of points with greedy. If you have an algorithm like simulated annealing, it has a loop that iterates over, you can control as a parameter how much time, how much work it's going to do, and you can increase the number of iterations. And so what happens with simulated annealing is you start at a random location, and then you iterate, taking steps, trying to get further and further down. You prefer lower steps, more work. But you've got to avoid getting caught in local minima. We'll talk about that in a minute. But essentially, if you give it a long amount of time, here in my example, you get 100 milliseconds and you only need 1 solution, then it has time to converge and get closer to optimal. Whereas if you give it short amounts of time, maybe I needed 10 solutions in that same 100 millisecond, it's not going to have as much time to get as far down in the solution space. And then you have quantum annealing, which is down here on the bottom, has this relatively enormous programming time. That's what the dash is. And then you can bang out annealing solutions, results of anneals, very quickly. And so the programming time is that line there where it's just waiting to get the chip set up. It's like programming and readout is kind of like I/O. You're setting up the chip and you're getting the answers off of it. In my example, the readout time is, the anneal time is about half the width of each dot, and the readout time is about the same. So if I were actually measuring anneal time, on this case, this is what it looks like in access time. Those 200 points that took 100 milliseconds would only take about 40 milliseconds because it would only be half a dot, so all closed over. And if I had an anneal time of 20 microseconds instead of 200, it would only be 4 milliseconds, so that line would move way over. And if I had an anneal time of 2 microseconds, which is possible, the total runtime would be 0.2 milliseconds, and indistinguishable from 0 on this scale. So anneal time versus access time makes a big difference to your perception of the computation time. All right, and as it turns out, when I was doing this literature review, it turns out that usually we think of characterizing performance as what kind of inputs does this solver work best on? What kind of inputs does that solver work best on? It's about matching the input to the solver structure. But what I realized is that it's really, in this case, with the quantum performance, it's about how you define performance, what kind of benchmark study you designed and what you're trying to measure that determines whether quantum annealing is going to look good against classical or whether it's going to not be outperformed. And so that was a profoundly useful insight. And so, for example, it depends upon the use case. So you're trying to simulate quantum processes. This is what my colleague Andrew King was talking about yesterday. You might be trying to do approximate optimization where you want to get a pretty good solution. You're measuring how far away it is from optimal. or you might be wanting to do exact optimization, which is how close, how long does it take you to find an exact optimal solution. It matters the structure of the inputs, whether they're physical inputs or logical inputs. The simulation cases are kind of in between. They're like physical inputs in their structure, but sometimes there's a little bit of embedding going on. And it matters whether you're measuring anneal time or access time, really, really fast or not so fast, in terms of what you're comparing to the classical solver. And so, you can, under these different cases, you can start classifying. You go to look in the literature, do you see a lot of wins? Are they usually winning? And this is what I came up with. In this space where we're doing approximate optimization, we can see that depending on whether it's a physical graph or a logical graph or anneal time versus access time, either the QPU is going to routinely win, or it can usually win, or sometimes we can say, well, as far as we know, it mostly, it can and it can't, but mostly it's a little more unbalanced, or a little more balanced that way. And so I want to talk about that transition from it's fabulous, yeah, it's okay, sometimes you can, sometimes you can't. Because once we can see what makes the difference in performance this way, we can start to generalize and understand the whole space a lot better. So here we go. I think we all know by now that optimization problems, you create landscapes, you get some kind of a logical input here, and a solution is an assignment of variables. In this case, I'll go with spins, +1, -1, to the nodes. And those make the individual terms in your objective function either positive or negative, and you're trying to minimize the total sum of all those terms. So it creates a problem landscape, we call it, where you imagine every possible solution is on the x-axis there, and the height of this landscape corresponds to the objective function value if you use that solution. So it's just a conceptual device for visualizing all the solutions and the quality of the solution you might get. And what we imagine is our goal is to try, in the approximation problem, is to try to sample from the low energy regions from the best quality solutions in the space, inside that pink band. We want to get a lot of samples from that space. And in my example, you can see the minimum, actually, it's not necessarily that it's sampling that distribution of the most common points. It's not necessarily the case that includes the optimal solution in the high probability zone of this distribution. So let's, in that context, think about this literature review, and this is where the surprising results were coming, for me anyway. Classical heuristics, we know that if you increase the runtime, you have to increase the runtime to maintain a good quality solution as the problem size increases within the problem size. But with annealing, in all of the literature I read, no one ever increased anneal time to account for larger n. It's always in these studies, and I say always, I say nearly always, I've never seen an exception. Anneal time is set to some convenient constant value that doesn't have anything to do with problem size. And also with classical heuristics, we expect this no free lunch phenomenon. That means that you have a heuristic like simulated annealing. It has a lot of parameters, and performance really matters. It really depends on what your parameters are set to. And you need to tune your heuristic to do well, and tuning can be quite expensive sometimes. And what you see with annealing QPUs is the solution quality that you're sampling some pretty close to optimal, pretty consistent. It kind of doesn't matter what tuning doesn't affect it all that much. So those are two very interesting differences. And basically, if we think about how they work, you can start to understand why this is. Classical heuristic search, here's some landscape, and you start at some random position, and you're trying to get downhill as fast as you can, as low as you can. And the bottom here shows, the fact is you can only see your immediate neighbors. You're making an incremental change to the random solution you start with, and I can go this way, I can go that way, I can go this way. You make a step, you prefer to go downhill, but you want to avoid local minima, so you've got to have some mechanism for backing up every now and again. And so it's kind of clear under this circumstance that if the size of your solution space is increasing, the number of different places in it increases exponentially within, then of course you're going to need to take more steps in order to get as far down. And I'll skip this no free lunch part, but basically the idea is I marked one in red. This is from a paper, has nothing to do with quantum. You can always get your solution to do well on one input, but if you try that same heuristic on same parameterization on other inputs, and it's just not going to work. So you're always kind of stuck in this, how much time do I spend optimizing my parameters? But qubits have these special powers of entanglement and superposition and so forth, and because of that, it doesn't work the same way. Instead of starting with this landscape and taking a step and then taking another step and then taking another step, what quantum annealers do is they manipulate the landscape, and the probabilities of the qubits are tracking the lower areas of the landscape. And because of superposition and entanglement, one register of qubits is representing the probabilities at which it's going to come back with a sample. And so it's just not step by step at all. And so I drew this great picture where it starts out with a flat landscape, all the probabilities, everything's in equal probable superposition. You know, the probabilities are everywhere the same. And then gradually during the anneal, the landscape starts growing up out of that flat region, and you start to see features defined, and the probabilities pool in the low-lying regions. They're looking for their ground state, and the highest probability is going to be the lowest energy state. And then at the end, you have the same landscape as before, but your probabilities have pooled, and they're all down there and that's where you draw your distribution from. So the point is that with quantum annealing, it doesn't really matter how big the landscape is. That's sort of how many states there are. It is wide. It grows exponentially. What matters is how high this landscape is in relation to the pink band, which is really a function of the hardware. The hardware and the location of the pink band doesn't vary input from input. It's the size, the height of that landscape when it combines with that gives you your probability distribution. And as it turns out, the heights in the landscape are more like linear or quadratic at most, but they're a slow-growing function of input size. And that's in contrast to the 2 to the n size stepping that you have to go with. So in this case, these histograms here are showing how that distribution varies with n. It slides to the right, and the blue line, the blue curve there is the growth of the center of that distribution with respect to n, and in this particular case, it's growing about linearly in n. So what that means is that on the really big inputs, classical needs a lot more time to take each step, or linearly more time to take each step in a good case. But you need to take more and more steps on the really large problems. And so here's the green one is simulated annealing. It needs more time to converge. Whereas quantum annealing, the QPU in blue there, has already, this is access time. This dotted line on the left is the lowest you can go because of programming time. And these are access times it's banging out. And you can see it's always been low in the sense of it doesn't start at a random solution and work down. You get what you get at the end. Whereas on large and small logical inputs, if it's a large logical input, here we can see actually in this case here, It's the largest logical input we know how to fit on the current advantage machine. If you give it a second of runtime, quantum annealing, simulated annealing has enough time to outperform the quantum samples. But if you give it a tenth of a second here in the middle of the graph, then that's a case where quantum annealing is doing better. So you give it less time, and quantum annealing can win because it just takes, on this input, it takes that much longer. So that's the crossover we're seeing. And then the bottom one here is a fully connected graph, 175 nodes. That's the most dense graph we can fit on a QPU. And you can see on this relatively small problem, both the greedy red and the simulated annealing in green are getting there faster because they're only working on a problem of size 175 variables. The quantum system, no matter what size problem you give it, it gets mapped to the hardware graph, and it's always going to solve the full-size hardware graph. It doesn't notice that some of the weights are 0 and some of the weights are not 0. It's always going to be solving the same kind of graph. So there's no mechanical reason why its runtime should depend upon it. So here we go. And the thing is, with advantage, and the thing is, we know with all of these different generations that every time a new generation of processor comes out, the quantum annealer gets better in terms of lower noise and higher energy scale, and it's giving you solutions, quantum solutions that are closer to ground state than they were before. So whatever the quantum annealing is doing, it's going to do it better when the next piece of hardware comes around, and you're going to see those times, those solution quality values, the samples go south. Whereas once you have a larger quantum annealer, you can embed larger problems, and all the classical solvers are going to be, their points are going to move north and east on those graphs. And that's where we're seeing this crossover point. So bottom line, can annealing QPUs outperform classical heuristics, and when would that be? What we're seeing, if you look at the whole body of research, is that when the inputs are large and the runtime limits are quite small, perhaps, those are the cases where we see quantum annealing systems returning better approximation solutions than classical. And so can they scale up? Yes. I mean, that suggests that the bigger the problem and the same runtimes or shorter runtimes is going to be better for quantum annealing. It's going to relatively beat classical just by standing still. So, look, I have 2 whole minutes left. So that's because the newer generations are faster and they're better, and you don't need any increase in annealing time, apparently, to make that happen. They're always, I got reasons for that, but I can explain why that is. And the classical solutions, you give them the same runtime and bigger problems to solve, their performances, their solution quality's got to degrade. And we expect this trend will continue to the new generations. There's no expected increase in access time. That hasn't changed since we started with the D-Wave 2 with 500 qubits. It's been a tenfold increase in qubit capacity. And the access time has pretty much remained constant for all that time as the generations have increased. And so that's why we on the benchmarking team are pretty optimistic about the future of quantum annealing and the race against classical.